O in lame cow factors, of course, stands for ocean currents, and we will see some overlap as we discuss the ocean currents today with our W is for wind. A lot of those same factors will impact both the ocean currents and the wind currents. As always, starting out with our essential questions, there are two kinds of currents that we're interested in for the ocean. We have both the surface currents and the deep ocean currents. And of course, we want to know, how do those currents impact the climate of an area? That's the whole purpose of our lame cow discussion, to figure out how do these different factors change the climate of an area. And of course, review, thinking about climate, we're discussing both temperature and precipitation averages for an area. So we want to know, what are these climates, what impacts them and drives them through the ocean, as well as how do they impact the climate, temp and precip of an area. So a quick intro to why ocean circulation is important other than climate change. We do know that ocean circulation does account for about 20% of heat moving around the earth, and that is, of course, like normal, just like we saw with the winds, from the equator to the poles. So we are seeing quite a bit of heat move around the earth with these ocean circulations. Okay, they're bringing the heat to the cool areas, changing the climate in some zones. Now, ocean currents are also transporting nutrients around the globe, right? If you're an organism that lives in this part of the ocean, you might be waiting for an ocean current to bring you your lunch or your seasonal meals, okay? So ocean currents do much more than influencing just weather and climate. Okay, they also are a big part of the economy, right? When we think commerce, we got to think about trade, we got to think about fishing. Okay, ocean circulation is a big part of all of those things. But of course, our focus is this one today, weather and climate, and how that heat is transferred around the globe. So we are focusing on two types of currents, the first one being surface currents. Based on the name, we know that happens to the top part of the ocean, the upper 400 meters. And we also have the second type of current, which are the deep ocean currents. And those deep ocean currents then fluctuate within the bottom 90% of the ocean. So the surface currents are a much smaller scale, but we'll find out they have a little bigger of an impact on climate. Starting with surface currents, let's talk about things that would impact a surface current and cause water to move in a regular pattern across the earth. We've already talked about this one a little bit. We've talked about the seasonal or the uneven heating. Right? Uneven heating changes both the temperature of water in different areas, and as we found out now, the temperature does impact the density. So as that temperature changes, as does the density. And again, just a reminder, we know that warm air and warm water are less dense. They tend to rise, where that cold air and cold water, as we saw in our lab, tend to be more dense and sink down. So that temperature creates differences in density across the ocean. Other things that impact surface currents are also gravity, wind, of course, is blowing the ocean water's top around, as well as Coriolis effect. Coriolis, again, happening because of the rotation of Earth. Okay. All of those things impact the regular flow of surface currents. There are other things that can impact the flow on an irregular basis, like boats, different schools of fish, earthquakes, things like that, but they don't regularly impact surface currents like these do. Okay, so starting with uneven heating, let's remind ourselves of a few things. Where would we expect to find the warmest ocean waters? Thinking about latitude on your graph here in your notes, where would you put a star showing the warmest ocean waters? Hopefully you're thinking somewhere around the equator is going to be the warmest. And of course we know the equator is the warmest not because it's by the equator, but because of the amount of direct rays that area gets throughout the course of the year. Much more direct rays shine on the equator throughout the year, giving it overall warmer temps, just like we see with the land. Okay, the ocean is getting the same direct rays as the land would, causing its temps to be highest. Okay, now we do see here on this color diagram that that warm water then flows to the poles, cooling down and returning back as cold currents to be reheated and cycling through these giant ocean current cells. That's what we're going to be looking at today. How are those forming? What causes their motion? And how does that impact the climate? Now, of course, impact of heating, because of that uneven heating, the equator, like we said, has the warmer temps due to the direct rays, and the poles are those cooler temps due to the indirect rays. Now, what's important to know is that those surface currents try to balance or redistribute that energy between the warm and the cool across the globe. They're bringing the warmer water to the poles, either the north or south, and the cooler water is being pushed back to the equator to reheat and cycle through. Again, as a surface current. Impact of gravity is an interesting thing to think about. The ocean isn't perfectly flat. There are pockets of the ocean where the water is heated and therefore expands, making a higher elevation in the ocean water. Okay, so we can see here on our graph that the highest part of the ocean surface here is in fact that warm red color. Knowing that is the warmer water, those molecules have expanded apart, causing a slight elevation increase. And we see the opposite then with colder water, because their molecules will condense we see a lower elevation created with that colder water. Okay, now it's important to think about this as small scale. If we look at the scale here, we're only seeing an increase of about 14 centimeters, a decrease about 18 centimeters. So we're looking at less than a foot of difference. And we're talking thousands of miles. This span of the ocean is from North America all the way to South America. So it's not like you see peaks and valleys within one small section of the ocean, but we're talking about a very large peak and a very long valley happening across the ocean. Now where gravity comes into play then is on this peak and valley. It will then pull down the warmer water towards the cooler water. So just like we see gravity happening here on the Earth's surface, it will pull the warmer water downward, causing a flow to happen with the surface currents. Wind is going to be a big impact on surface currents. Knowing that wind is quite frequently blowing around on the ocean surface, we know an impact is inevitable. But the wind, of course, is only acting on the very surface of the surface currents. In fact, the upper 100 meters of the 400 meters considered to be surface is affected by the wind. Once that wind starts to cause drag on the ocean surface, those ocean molecules will work their way down through contact and friction, creating a small force of motion in those lower depths. And we can see here that the force, the amount, is lessening or weakening as we get further down in the depths of the ocean. So we see that top layer causing drag to those underlying layers but with much less force. The speed of the force is much lower the deeper that we go in the ocean. So the surface current is strongest at the top where the wind has direct contact with those water molecules, but the further down we go, the lower or the weaker that current is. Okay, Coriolis, of course, is our last impact on surface currents. We talked about Coriolis with wind, just a few reminders. Again, Coriolis is happening because of the Earth's rotation. And we know that each hemisphere causes the wind to curve ever so slightly or deflect because the Earth spins underneath those air masses moving throughout the atmosphere. We see in the northern hemisphere a slight curve to the right, and in the southern hemisphere a slight curve to the left. That impact is going to be mirrored for ocean currents. They work in a very similar way. Okay, we notice that again in the northern hemisphere, those ocean currents have a slight curve or deflection to the right. And we notice the surface currents in the southern hemisphere have a slight curve to the left. Okay? Rather than moving vertically, like we see the convection happening in the atmosphere, this is happening on the surface. So we get oftentimes gyres or flat convection currents that are forming within the surface of the ocean. We can see all those currents back on this diagram. Again, looking at the northern hemisphere, we've got currents that curve to the right, and in the southern hemisphere, we have currents that curve to the left, all because of the Earth's rotation. Now, these surface currents directly impact the heat transfer on the Earth, as well as the climate of the cities that they transfer that heat to. So what we notice is that surface currents play a significant role in bringing that heat energy from the equator towards the poles. Just like we've seen several times already in that diagram. Cycling is going from the equator to the poles and back, balancing out that energy within the ocean. Now, these currents sometimes serve as a heat source to cooler overlying air. For areas that don't have the warmest air temperatures, this warm ocean water can come in from the equator. And when that warm ocean water comes in and comes in contact with that cool air, it acts as a heat source, supplying some heat to those coastal cities. What we see then is both evaporation and condensation affected. Evaporation and condensation help with that heat exchange when the water is turning to a vapor and the vapor back into a liquid. So surface currents impact climate fairly regularly. Let's look at a few examples. The California current is a big example of a coastal area affected by the temperatures of ocean waters. California current, of course, running down the western edge of our continent, and we can see here that this California current is coming from the Arctic area. So we can assume the temperature of that water is going to be cool. We see a lot of Arctic motion and Arctic water traveling down from the North Pacific Ocean, that west coast of North America. The California cities tend to then have cooler temperatures than normal due to that cool ocean water coming in contact with the warm air, cooling it ever so slightly. Okay? As we see again, that Arctic water working its way down the coast, we know that these coastal cities along California, close to the equator, should have warmer temps, but they're cooler slightly than cities with similar latitude not on the coast because of that cool temperature being brought in by the ocean currents and the Arctic waters. Again, we can see here that the coldest water is staying closest to the continent due to the flow of the current. Those colder waters supply colder temps to those coastal cities. So the California current actually cools down those California cities. As we can see, the coastal cities are a little bit cooler than the inland cities. We want to know why. What are two climate factors that make those coastal cities cooler than the inland cities? We just discussed one. That's ocean currents. Okay, ocean currents make the temperatures cooler. See if you can come up with that other one. Why would these be a little bit cooler, more regular than a peak of the cities that are further inland? See if you can come up with that second climate factor making the inland cities have higher temps than the outer cities. Another area greatly affected by ocean currents is Western Europe. Looking at this diagram, let's think about how does latitude affect climate, and let's predict which city would be cooler and which would be warmer based on latitude alone. So we have two choices here. We have Canada at the 44-degree latitude line, and we have Europe at the 52-degree latitude line. Now, of course, thinking of this question, how is latitude affecting climate? We know when we're closer to the equator, we have much warmer temperatures. Further from the equator tends to be cooler. So with that prediction, we should see that Canada is warmer, being closer to the equator. That's our prediction. And Europe being a little bit cooler because of its distance from the equator. But if we look at the actual data, we're going to notice that the Canadian temperatures, the average high is close to 0 and 2 degrees compared to the coastal cities of Europe having temperatures of 7 and 5. So what's happening to cause the higher latitudes, those warmer temperatures? As we can see here, there's a current moving from the Gulf of the United States up the eastern coast and crossing over here to Europe. What that does is actually brings warm water across to Europe, all the way from the Gulf. That water retains its heat all the way here, causing the Europe rather to be cooler, to be slightly warmer than those lower latitudes. Canada ends up being a little bit cooler from its latitude and not being affected by that warm Gulf Stream. So despite the fact that Canada has a lower latitude, it is in fact not warmer because the United Kingdom and Netherlands here are impacted by that Gulf current that's nice and warm. So we see those two smaller warm water currents combine together to bring all kinds of warm water and warm ocean currents to Europe. And as that warm Gulf Stream continues its path hitting these European cities over here, what we see is warming of the shores of the British Isles, or that Western Europe area. The last current we want to talk about today is just the Antarctic current. It's basically circling around itself. It is one of the largest surface currents on the globe, and it moves most amounts of water circling around Antarctica here. Now, of course, being at the poles, this is going to be a very cold current, but it's moving simply circulating west to east around Antarctica, keeping that cold water in that area, not skipping up to the equator to warm up, but keeping all of that cold water circulating around and kind of insulating Antarctica to keep it cold and frozen most year round. So here we can pause, take a look at our essential questions. We've just discussed surface currents and the major way that they impact the climate of an area. So you can pause, describe each of those 4 factors that affect surface currents, and then how do they impact an area? Give one of those examples we discussed of California or Europe. What does the temperature of that water do to those coastal cities in that area?